So we'd like to move to next speaker, also wonderful speaker from Italy. So next is Antonio Bicchi, is senior scientist at Italian Institute of Technology in Genoa, and also the chair of robotics at the University of Pisa. So please.
Good morning. Wonderful conference. Thank you very much for this treat. So the talk today is about hands, of course, and I start with this painting by Caravaggio, the car sharps. Everybody in the arts critic agrees that this is really a picture about hands. Hands are the most difficult thing to paint, and here Caravaggio showed all his mastery. Hands are used here for supporting, for communicating, for exploring, for holding, and finally manipulate things. So this is a nice framework to show how complex it is. So now let me go back a little bit in the spirit of this conference, I think, 30 years ago. And what was the grasping literature? Here are a few examples from the literature. So one thing you notice, there are no hands. The second thing is that there are rather abstract models of grasping. At that time, we started inquiring some theoretical underpinnings of grasping. So we clarified a few things. For instance, let me go through some details. What is form closure? I don't know how many in this room or how many in the young students recall about form closure. Form closure is the property of blocking, basically, an object by virtue of contacts. Imagine the pink dots as fingers. This object is not form closure. This is partial form closure. This means that there are motions that are allowed. And if you do an analysis of this is basically a linear program that you can solve, and you can find that the set of motions that are allowed by a given set of contacts is a cone, and you can give a nice geometrical description of that cone. A next step was force closure. What is force closure? Is when a hand and an object the hand can resist all external disturbances. So if I squeeze this, I can squeeze as far as I want, but I can prevent any motion of the object. That would be force closure. Of course, it takes friction, a model of friction. It takes a balance equation for the wrench that is exerted by the external world on the hand. And you have to verify all friction constraints by squeezing more to avoid slippage, something that we do now very often with hands. The question here was what squeezing forces can a hand really apply? Because hands are an integral part of grasping. That was not so clear at that time. And it is the hand, we realized that it was the hand that made the difference. So for instance, this object, you only have contacts. Is it force closure or not? Can it be squeezed so as to avoid any motion or not? The answer is unclear unless you have the hand. So this hand can really squeeze the object and prevent any motion because of friction. This hand could not, because there is no degree of freedom of the hand that could squeeze the hand. So, okay, this is the observation, and then the analysis of this was, well, the problem is ill-posed if you only do equations of balance, static balance between the external forces, the internal forces, and the torques at the joints. So this is ill-posed for whole hand manipulation, and it was realized that you really need a soft body, a model of softness in the body to understand the physics. And that is now a solution. So you can find how the forces distribute and how they can be modified and decide whether this can be done or not. So now, problem still remains. What are hands good at? How far are we from human hands? Very, very far. Very, very far. So 10 years after doing that kind of work, I started reconsidering with some frustration for not being able to go much beyond theory. We started looking back and saying, okay, but I would really like to do something. And we came up with this idea of soft synergies. That's the idea of a geometric template, a primitive of motion that are the synergies that attract the hand while the physics of the interaction with the environment repels the hand and decides on the shape, on the final shape of the hand, so that the same primitive can lead to very different endpoint results. By the way, the analysis of this was only possible because we understood that this is a whole body, a whole hand problem, and we understood that because 10 years before, we had those equations. There are other interpretations that are very nice in neuroscience, in motor control. Anatole Feldman calls these equations equilibrium point. The practical conclusion is that the environment manipulates our hands. The shape of the hand is dictated by the environment, and kids know well how to use this. So if you look at this, this girl, that's not an ordinary girl. That's Tamim's daughter. So it's probably smarter than average, but she managed this very simple hand to pick up a coin out of a table. The hand was deformed on the table to pick up the object. And here is another demo of Manuel Catalano using the hand to do things that the hand could not do if it was not used in the environment to prepare its shape to do things. So question is, can a robot do the same? Can we use the environment to manipulate our own hands and the environment finally? There are two types of approaches that I will review quickly. Data-driven approaches, of course, they do not require precise models of the object to grasp, but require large data sets. Here is a work that we presented recently, also got some recognition. Idea is that you get an object, you get a point cloud, you do a bounding box decomposition, you use Danica Krajic's nice idea of a bounding box decomposition, and you only teach a person, through a person, how to grasp boxes. So you have a large repertoire of boxes, you learn how to grasp these boxes, and then you apply to any object. So basically, it goes like this. You look at the boxes, you score the different grasps, you put the hand in the picture, which is fundamental, and then you have quality measures, some for the quality of the box, how close it is to the point cloud, some for the wrench quality, some for the alignment quality, some for the collision avoidance, and in the end, you have this neural net that computes what is the best grasp. So interestingly, with the hand that we are using, we are able to do many, many grasps, and the results are good. It outperforms the state of art. Good news is that it can also be used with other hands, for instance, even with Frank Agripper hand, where we showed in this paper that this method outperforms DexNet or others pretty well. There are harder tasks, though, where I don't think that pure learning is still good at. For instance, you want to take a box out of a shelf and put it on there, or to take that brown box from that position and bring it in the desired green position. Or take the last box, the black box, under the red bricks out and place it out there. So how do you do about these things without a plan, but just by finding the plan? And in this case, analytical approaches have some advantage. They do, of course, need a model or need good data, but they offer guarantees on the stability, and they have no corner cases. Once you have an analytical solution, you know where it works. So there are advantages. And here is the task, for instance, of getting the box, the book out. You are using basically the form closure cones that I discussed before to describe the space of free configurations. Then you search the space through RRT, basically. And then you apply force closure analysis to determine how to take the box out of that, how to make it roll, how to avoid slippage and eventually to grasp it out. So here are a few experiments. First are the recreated scenarios. You see, for instance, in the middle example, what you do is you decide that you would push the box out of the table and then find a grasp, and place it whole. And in the other cases, you're pushing it out of the box. None of this was pre-programmed. All of these behaviors are found by the algorithm itself, out of that search mechanism that I showed. Of course, no plan is perfect. No execution is perfect, so you also need reflexes. And here is a very short snippet about reflexes. So if you want to grasp even the simplest object, imagine this is the book before, if the object is displaced a little bit with respect to your plan, even a little bit, even a forgiving hand like this one will not grasp. So then, but we can repair. So this is the method that we proposed recently of having a grasp that stays as close as possible to the planned grasp, but pivots around the first contact until a second contact is reached, and then pivots about the two, and then does this enveloping grasp. So I have no time to go into details, but this is just to tell you how important it is to add reflexes and sensing to the nominal plan that we've come up. So to conclude, can robots do the same as this girl? Can we just reason about picking a coin and take it out by exploiting the environment and the constraints that the environment proposes? Not by far. We are not there yet. I think this is a large agenda. I think in many things that Raja just said, I find myself on a much more practical or down-to-earth side, but I agree with what he said, and of course I agree with Oliver said yesterday. But it is an interesting research program. The grasping problem is not solved, and indeed, Matt, a grasping problem is there, I think. So thank you very much for your attention.
Thank you very much. Thank you very much for giving wonderful view to grasping. We would like to have short questions from the floors while changing that laptop. Anyone's? Okay, please.
Hi, Professor Bicchi. Just to say, I read a lot of your papers when I was in grad school. Love them a lot. So quick question. Most of the commercial robots I see, they have two fingers. They are grippers with 2 fingers. Just curious, what are your thoughts on robots for household tasks? How many fingers would you put?
Well, you asked me, of course, I have a conflict of interest. I think that the best hand is our hand, like everybody here. But it depends very much. I mean, anthropomorphism of the hand is not a trivial, is not to be taken for granted. You saw here that some of the methods we apply to hands and some we apply to grippers. Eventually, I think grasping is the same problem. Once you have, but you have to take the hand in consideration. In service, I tend to think that a more anthropomorphic hand is useful, not just because it's better, but because the environment is designed for our hands. Handles are made for hands, right? And everything else is made for human hands that in our houses. So it's very likely that the shape of the hand is best suited to grasp the everyday's daily activities objects.
Thank you again. Thank you.